Welcome to today's lesson. In this first tutorial, we will be able to describe a geometric pattern, and we will use the first of the three geometric formulas. So we are in section 12.3 and 12.4, and now we're talking about geometric sequences and series. A geometric sequence is when each term is found by multiplying a constant called r, and r is called the common ratio, to the previous term. So this time when we're geometric, we are multiplying, and you'll see that the sequences get pretty high pretty fast here. So example 1, we've got our terms 4 and then 12 and then 36. And you can see, hopefully, that we cannot be adding the same thing because 4 plus 8 is 12, but if we continue to add 8, we wouldn't get to 36. So this is not arithmetic, this is geometric. We are multiplying by 3 and multiplying by 3 again, and therefore we're continuing to multiply by 3. So r says state the common ratio. R must be equal to 3. Part B says find and label the next three terms. So if we continue to multiply by 3, 36 times 3 is 108, and that would be a sub 4. That's the labeling part. Multiply by 3 again, and we are at 324. That would be a sub 5. Multiply 3 one more time, and we are at 972, which would be a sub 6. Now, sometimes it might be a little difficult to find r. So if you're ever having trouble finding r, just understand that we can take any two consecutive terms but divide backwards. I usually just take the second term and divide by the first term to figure out what r is if I'm ever having trouble finding r. But I can take any two terms. I could take the second term and divide the first term. 12 divided by 4 is 3. I could take 108 divided by 36 and I'd get 3. I could take 972 divided by 324 and get 3. So any two consecutive terms divided backwards would be the value of r. So our first formula, and the only formula in this tutorial, to find the nth term of any geometric sequence, we have an a sub n equation, or a formula in this section as well, and that will be a sub 1 times r raised to the n minus 1 power. That's the formula to find any term of a geometric sequence. Notice this time that our first term is a coefficient, that r is a base, and that our exponent has our variable n. So if I wanted to complete part C, it says write a rule for the nth term of the sequence above. So we're still talking about example number 1's sequence. So if I'm writing a rule, all I need to do is plug into this formula. So a sub n, that's going to be my rule, is going to be my first term, which we can see is 4, times my r, which we found was 3, raised to the n minus 1 power. And that is the rule for that geometric sequence. Let's look at example 2. Instead of giving you the sequence, I'm going to give you some parts of it. It says, find the first 5 terms if a sub 1 is 5 and r is negative 2. Well, a sub 1 always represents our first term, so we must be talking about a sequence that starts with 5. If r is negative 2, now I know that we're talking about a geometric. R is something that we're multiplying to get from term to term. So if I'm multiplying by negative 2, 5 times negative 2 becomes negative 10. If I continue to multiply by negative 2, negative 10 times negative 2 becomes 20. 20 times negative 2 becomes 40. Negative 40 times negative 2 becomes 80. I believe that's it. 1, 2, 3, 4, 5. I've listed the first 5 terms, and now we can see a special property that can happen for geometric sequences. Our terms might alternate sign, and that will happen when R is a negative. So that's kind of interesting. That's something that will never happen with an arithmetic sequence, but geometric, we can alternate terms. Part B, it says write a rule for the nth term, so I know I'm talking about a sub n, and I'm really just plugging into that formula. The first term is 5, r was given as -2, and we're raising it to the n minus 1 power. So that is the rule to describe the geometric sequence above. And now we have a rule, we can find any term we want. If we're looking for the 12th term, all I need to do is understand that n is going to be equal to 12. So if I'm looking for the 12th term, that's a sub 12. I'm going to use my 5 and my -2 and raise it to the 12 minus 1 power. It's as simple as that. Now I would actually plug this into the calculator as 5 times -2 to the 11th, just so I don't need parentheses around here. We all know that 12 minus 1 is 11, and when I plug that into the calculator, I will get -10,240. So you can see with geometric sequences that the terms can get to very large numbers, or I guess very small numbers in this case, very fast. With our arithmetic, when we're just adding, the terms don't get that high that fast. These terms get very high, very great because we are multiplying. Let's move on to our next type of example. Example 3 looks similar to one that we did in the previous tutorial. This time we're finding the two missing geometric means. And the geometric means would be the two numbers that would fill in this sequence such that the entirety of this sequence becomes geometric. So I know that geometric we're multiplying to get from one term to the next. I don't know what r is, but I know that I know that 3 is 3, but I know that 3 times r is going to be what the next term is. Whatever r is, I multiply by 3 and I get this. And then the next term, I would have to take 3r and multiply by r. So 3r times r becomes 3r squared. And the next term, I'd multiply 3r squared by r, and 3r squared times r becomes 3r cubed. And that's what we can use to solve for r. I know that 3r cubed is going to be equal to 24. And if I'm going to solve this equation, I would probably divide by 3. So I'd have r cubed is equal to 8. And that reminds myself of a perfect cube. Take the cube roots and r must be 2. And now we can go ahead and confirm that. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. So we found the two missing geometric means. What if I go and do a little review and say, what if I wanted to know what the arithmetic means were for the same two numbers? Well, arithmetic, we're adding, so 3 plus d would be my next number. And then 3 plus d again, or rather 3 plus 2d is my next number. And then 3 plus d plus d plus d, or rather 3 plus 3d, is my last number, or is 24 at least. So 3 plus 3d is equal to 24. Subtract the 3, and 3d equals 21, and therefore d is 7. What we're adding becomes 7. So 3 plus 7 becomes 10. 10 plus 7 becomes 17. 17 plus 7 does indeed equal 24. So look at the difference between these two. If we're looking for geometric, we're multiplying by something called r. If we're looking for arithmetic, we're adding by something called d. Do that until we can set up an equation to go and find either r or d. So we're finished with geometric sequences, and we're moving now into geometric series. So again, I want to make sure you understand the difference between a sequence and a series, and that is not it. A sub 1, A sub 2, A sub 3, A sub 4, dot, 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 dot. This represents a sequence because the numbers are just separated by commas. That same sequence of numbers written as a series changes the commas into addition signs. And a series is when we are adding terms together. Thanks for watching me in this tutorial, and we're going to stop it there and talk about the series now in the next tutorial, and I'll introduce the last two formulas. Thanks for watching. See ya.